Lunch and learn in the annex building in about 2 minutes. Again, lunch and learn 12 noon in the annex building.
Right.
Well, that's good if you know Johnson Control.
Sometimes
we
things
need
work
that.
out best.
Oh, yeah. It's huge, man.
Yeah.
I don't want to be
Right.
Lunch and learn in the annex building in about 2 minutes. Again, lunch and learn 12 noon in the annex building.
It's a bit of a
That's
delay.
good, that's good. Okay,
Hey,
nice.
There's a delay or there's a...
I'm streaming it on YouTube, so there's about a 7 to 10 second delay on the recording and then it's streaming. So
It's up to you. I don't know what you're gonna do.
Known for what?
How long you been doing
18
it?
years.
And they got food over there.
Alright.
how we doing?
All right.
Salad, onion,
Hey,
there's pastor,
Okay,
sounds good.
cebolla.
very chancy.
So how many people do we have?
I think we got like 15. So we'll
15?
see. Yeah,
That's great, because now everybody can have seconds.
yeah.
Oh, okay, yeah, I like that.
Well, what's funny is when I messaged you last week, I had this scheduled for last week.
Right.
Which is weird because I told you this week.
Right, the 29th.
And so Friday morning, I was like, "Hey guys, sorry, like I put it on the wrong day, and I shifted it to this week." So I think we're missing a few controls guys that are starting up the job.
That's not a big deal.
But you know,
I figured, you know, I ordered for, just in case, I said I'm gonna order for 26 people.
Yeah.
And I said, and sometimes I get more people and then we run out of food.
Yeah.
It's better to have more than not enough.
Agreed.
Well, the food is there, help yourselves.
I came to the stark realization that I know nobody that works in this side of the.
I can give you a tour.
Yeah, but
Welcome to the annex.
Yeah, it'd be nice to. I mean,
Wait, you've been-
all the whackets and stuff. I'm like, oh, who are you? Who are you? Who are you? I thought I used to know everybody's name.
Well, you've been on this class, coming to this class and never like met anybody that works over here? I mean, I even met John.
Oh yeah. Okay.
He told me that.
To be fair, I also don't know half the controllers, and I work over here.
So okay.
So,
So that's the.
I'm also highly
Don't feel that
antisocial.
Yeah.
Yeah, it's a weird.
Yeah.
I make no effort to do so.
He said, you know,
I haven't talked to him here.
that he was on
So much effort.
How you doing? How you doing?
Good, good.
Good, good.
You got it done first. Pressure's not.
Did they announce who was sitting at the desk?
They did.
They did.
I didn't understand the company.
Yeah. Like they kind of grumble out.
Yeah. The
Like,
lunch and learn from room is happening now. Lunch and learn from room, not happening now.
I didn't tell her, so she probably just kind of.
lunch and
No, exactly.
Yeah.
Exactly, it doesn't matter who's in it.
Excuse me.
It matters. Sorry.
No me quise sentar muy pegado allá. It will be next to John, and John is a little bigger and taller.
Plus, I have a sneaking suspicion that once they find out what the food is, like, that's why you wait like an extra, because there's like a second wave like 3 minutes back that's always like, oh, dude, they had Chick-fil-A, or they had Mexican food, or they had this, that, you know, but if it's, you know.
We did a lunch and learn a couple of days ago, and I ordered a taco.
Uh-huh.
And we had to wait for about half an hour before they emptied the trunk. It was sitting outside, and everybody's just coming by. They're gonna, whose food is that?
Yeah,
Nobody
we got
calls
it.
for lunch and learn, you're gonna have to wait.
They wanted to get in on it, right?
Yeah.
I'm looking for you.
It was like, can we get some?
I'm in the room right now.
Oh,
Can't go wrong with street tacos.
oh, Jeff,
Oh, yeah.
you don't do any more classes, right? You don't do more classes at the,
Yeah, I stopped teaching it
I haven't seen it.
you know.
It's been a minute.
It's the,
Keep me, they keep me locked
some
up.
kid.
Kind of unfortunate. If you notice on my side glass door, the lock is on the
When you talk
outside.
to them?
No, I know that,
Yeah, the lock
they
is on the
moved-
outside, the lock me in my office.
Oh, my God.
Yeah, it's like,
So,
Where's
gotta
that
take the
water
message
park?
and someone, when the number comes by and just
oh,
calls me
the
in.
Santa Monica?
No, the one on the 7, 210 freeway.
Oh, yeah, San Dimas. San Dimas.
It's like a charging virus.
Yeah, I see.
They don't have the offices that you
Well, it's
downtown LA.
been really busy with this,
Which was a good place, that place was kind of sketchy.
That was scary, well,
I mean, we're not the engineer on it.
you were glad you parked in the parking lot, right?
Right.
I'll say the parking lot would not be good.
Save the hardest it's made.
Yeah, if you had to park in the street, it was gonna be
You
a
know,
challenge.
Yes,
And
Yeah.
your gun.
And just
I think you did.
asking, just,
I did see a lot of guys
you
parking.
know, take a step back and just
It's
ask some
always
simple
sketchy.
questions
Yeah,
and
sure.
find out.
No, I'm on the over here, I'll give you more.
Oh, yeah.
No, it's good. Yeah, I can come over there. But I'm curious that you might need a little more room than me.
I was just trying to figure out what the other sheriff was.
No, I must have, there was none over here.
What they're usually want.
Okay.
They have the cameras
So, you know,
there.
so there's been a lot of.
Fair enough.
You're not that old, Jeff.
Yeah, but we can put it on.
I know their defense, I don't think they had very good.
Well, they use all
I had
kinds
some
of-
project.
I used to work
They're
like
in
one low
Seattle or
What do you mean?
Yeah, they've flown down here a couple of times, one of them was
Retired.
based on.
Yeah,
Your
more.
recommendation.
And you're making right now.
Really?
If you retire, you make more.
Just go through it. I won't even-
But what am I gonna do?
So besides Mikey, what else do you watch?
Sports was. I used to play a whole bunch of sports growing up. Like I played rugby in high school and soccer.
You play soccer?
I used to, yeah.
Because they're
Yeah, I was a goalie for 3 years.
Of course you would.
Right, there, I don't know if you know the one.
As tall as you are, would be with a heart keep like this, it's supposed
He
to
was the
be.
engineering manager.
Yeah, I guess.
Because there was, I mean, I play goalie, I play
Years ago, I took him out
goalie,
for
like
dinner.
an older, league, like 35 and over, and I never played goalie.
You're either small and really, really fast, or big and lanky.
We had one of each. Yeah, the other guy,
I was
the other goalie on my team was like short, smaller, like a quick guy. And he would like make these spectacular diving saves.
You're just like,
I've been more like up here.
Yeah. I had a lot more reach, so it didn't look
Not a
quite.
good idea.
Not right now.
you made it look Netflix though.
Like, he was a little harder to reach.
How about the people retired?
Like, just for the ones that going up high. It's just already not that big also, but it was fun though, it was fun, I never done it, I was forward.
Yeah.
I was different.
Yeah, it was-
I feel like I was fast.
Okay. I was usually a defenseman. And then in 8th grade, we needed a goalie. And I was like, oh my god.
To slow down.
And then I started playing high school.
It's fun.
Yeah,
I like
they
it.
tried to
Me too.
add 4-inch internal line.
Yeah, but then I messed up my
Through existing
last year.
high school rules that
That makes it hard.
I have that same story, except change soccer with playing clarinet.
2 days a week.
Yeah, we need a clarinet player.
I had the same thing.
And he's making.
accomplished.
So he called me.
Is that easier introduced?
And so we had to give him the biggest opening size that we
I
could
did.
get with
It was.
their depth.
Now I'm helping.
From there, they knew if they had to have a 4-inch liner.
Yeah.
I get my
I
hours,
did 8 inches
whatever I
of
want.
each
I always
dimension.
play on
And they give me an amount of money that
You know,
it's
they did
all
get to see it, I was, oh,
working.
shoot,
I think I
have a 4-inch liner, double the
I
air.
just played that game.
So slowing it down.
Hey, because coming to the
and then I started playing soccer.
It's gonna be all about,
That's wild.
and I just,
So-
like,
Being interesting is
Really, I just,
His name
I just
is.
went back to my ACL.
Hey, Miro, can you get me a Sprite?
Someone.
Sure. I used to play softball in high school. We had like an engineering league.
Yeah,
So I played once a week. This one. I enjoyed it.
Yeah, thank you. I'm kind of trapped back here.
I just like
Thanks.
a month away.
We have more and stuff.
No.
Call them and just, we'll get it to you next week.
I don't know. I brought three panels, I don't know, I have a whole box in the car if anybody wants more. But yeah, we have a lot
Can't promise not to be ever wide.
Yeah.
Stick guys like it. Trying to get over there. What's going on?
I'll get it started.
Be straight. Go ahead.
Do you want to just start?
Alright, let's get it started, guys. We're almost 10 minutes into the hour. So good afternoon, everybody. My name is Carlos Samron, and I'm the district sales manager for Belimo in Southern California. I cover from Santa Barbara all the way to the border with Mexico and San Diego, and the border in Arizona. So it's a small territory, but it's huge. Trust me. So I've been with Belimo for 9 years. I haven't met a lot of you, a lot of new faces, and I will try to make it over more often if COVID allows it, because I know everybody's working from home and we lost 2 years of our lives. But in the meantime, I'll pass my business card around and let you know. I brought taco bar today. I hope everybody likes it. It's got 5-star reviews, and I think that's the best way. So I have some new catalogs. If anybody's interested, I'll be passing my business card around. If anybody needs me, I'm pretty local. I'm out of Riverside, so I'm a stone throw away. It's a short 2 hours, 3 hour drive.
Exactly. You know, it takes like an hour and a half. Right there, but so far away.
But thank you for being here. I really appreciate it. At the end, I hope David can mention that we do have a whole line of sensors that now we have added to our product line for the last 40 years now. I'll probably do another lunch and learn just to let you know what is new within Belimo and what we're making ourselves. So, David Kendall, he's our regional applications consultant. He is he flew in from Denver, and he has been part of the engineering group that has designed Belimo's line of valves, including pressure-independent valves. So, he's our hydronics expert. I don't want to take too much. I already talked way too much. So, here's David.
Thanks, Carl. I do these classes for a whole bunch of sales managers, and they always buy crappy lunch. And so, like, when Carlos does this, I'm like, this is great. Like, a huge crowd's going to show up, but then everybody's busy, like, making out with their food. All right, so my name's David. I worked with Belimo forever, and one of my first jobs was designing control valves. So we're going to pretend that in the course of this conversation, everything I tell you about I'm responsible for probably isn't real, but let's just start there. The reality is there is a little bit of overlap. So I started working at Belimo in 1998. Belimo released their first pressure-independent valve in 2001. We released the CCV in 1999. So I was there when cool stuff was happening. I don't know that I'm responsible for it. 1998 started to be a long time ago now, right? That's 24 years ago. But the reality is, in the last 24 years, so many things have happened in the world of control valves. If we're not paying attention, we might not know what they are. And that's what we're going to kind of talk about here. I just want to make sure you guys know what's out there. Whether you use it or not, that's a whole other subject. But let's start at the simple place. We're going to use the staircase as our feature benefit staircase. And we'll start with standard control valves. So if you're not a valve guy or you just don't play in the industry that much with the product, this is a characterized control valve. Belimo reintroduced this in 1999 and changed how everybody did business in the industry. It's a characterized ball valve. We'll talk about that in a minute. We're going to use this as a representation of all regular control valves. So I could have put a globe valve or any other kind of valve up here. We're going to call this something very specific. We're going to call these valves position control valves. And I use that term because when we send a control signal, what we're controlling is the position, in this case, of the stem of this valve. How much do we rotate? In reality, what we're controlling is how big is the opening that the water goes through. Okay, we've been doing that for like 100 years. We're all pretty versed on that kind of thing. That's going to be sort of our lowest tech, lowest reward type solution. Up from there, that's supposed to stay there. That has something to do with the video. You broke the whole thing. You're fine.
You're fine.
Start over. Okay, my name is Dave. All right, so this is an electronic pressure independent valve. We call it the EPIV. It's irrelevant. Any pressure independent valve we could put up here by any manufacturer. So we're going to take pressure independent valves and we're not going to call them position control valves. We're going to call them flow control valves. Now that term is there for a real specific reason too. Now each value of the control signal is correlated to a specific GPM. So think about the difference of that. I'm controlling how much water can go through an opening this size. Anybody have any idea? I don't. How hard are you pushing on the water? What's going on? But basically if I push on this opening with 1 psi of pressure, I'm going to get a little bit of water. If I push on the same opening with 50 psi, it's going to look like you knocked a cap off a fire hydrant. That type of technology, we don't control the opening of the valve, we control how much flow gets to the coil. Whoa! That's a really big difference in what we're controlling. And how about, what's our goal? We're trying to control how much heat is exchanged? Well, how about we just control how much water goes into the coil? Hey, thank you, I'm done with my presentation. All right, so let's put that guy up there, that's pretty good. At the end, we're gonna talk real quick about this idea of smart valves. This is the Belimo Energy Valve, if you've ever heard of that. It's a full BTU meter strapped to a control valve. We do all kinds of crazy stuff with it. But we're going to put this at the top because the reality is that right now, if we want to, we can determine the least amount of water required to satisfy any given load in any space. We have the technology to do that. We simply choose not to. We don't need to in all cases. It's not efficient. It's an expensive technology. We can make a lot of excuses. But the reality is that we can correlate your control signal directly to how many BTUs you want to extract from the space. This valve can make the coil and the valve into a single piece of equipment that we're controlling the output to. So we're going to use the word smart valve, but if we want to go position control, flow control, we're going to call this power control. The control signal can just say, do 5 tons. Done. All right, let's start at the beginning. Position control valves. Basically, we're talking about ball valves and blow valves. The ball valve, we need to be characterized. Why do we want a ball valve characterized? Well, if we take a standard ball valve and we open it just a little bit, this is what happens. The ball creeps open, and I have a fairly large opening here. That means lots of water's going into that coil. Good thing, bad thing? Bad thing. I'll show you why in a second. When I first started working at Belimo, they stuck me in the little lab in the back of the building in Danbury, Connecticut, and they said, start carving these discs. We need to figure out how to make an equal percentage flow characteristic. We literally were shaving them with X-Acto knives and sandpaper. Why is this good? Well, now when I open the valve, I can control whatever cross-sectional area I want. If I'm right here, I got this tiny little opening, and I control nice, real low flows. Before the characterization of the ball valve, nobody used ball valves. They're super cheap, they're inexpensive to make. You can manufacture them by the millions in a big old hurry, but they opened too fast. So nobody ever used them. Belimo in 1999 and Griswold in 1999 figured out the same thing at the same time. I'm pretty sure our lawyers still have lunch about once a month. I don't know how that happened. All right, why is this a big deal? Why do we give a crap about opening a valve slowly? Well, this is a coil curve. This is the only physics in this whole thing, and there's no test that you know about, so don't worry about it. Flow going this way. I'm increasing how much water goes through my coil, and then I'm measuring how much heat exchange I have. What's the first and most obvious thing about this? There is not a linear relationship between flow and heat transfer. Yikes. That sucks, because how can you tune a PID loop on this shape? Answer, you can't. So, what we've done with control valves, this is just the natural physics, by the way, of a coil. Coil's a long piece of copper tube. If I put a little bit of water in there, real slow, real cold water, it just sits in there all day long, making its way through there. I'm blowing air across it, it's pulling the heat out of the air, it's condensing water out of that air, and that little bit of water that's going through there real slow is doing a lot of work per molecule of water. So that's why I have small change in flow, big change in heat transfer, as opposed to all the way up there, where I have huge changes in flow and not much change in heat transfer at all, because now the billion molecules of water and each one's just racing through that coil. That's why we have this shape. Let's design a control valve. That's what the disc is for, right? Really slow flows down here. Really slow flows allows us to navigate the steepness of this curve. Here's something you probably didn't know. A control valve that's halfway open produces somewhere between 20 and 25% of the maximum flow rate of that valve. Anybody go, yeah, I do that. Anybody? Halfway open control valve, tiny flow. One guy. That's a good percentage. I'm still winning.
He's lying.
Okay.
I don't know that.
So why is this important? 25 to 25%. Let's go out the flow, 25% up there. Oh, look, half the heat exchange. What I want to do is take these two curves and just mush them together and create some sort of linear response between the control signal and how much heat I exchange. Now I can tune that because it's nice and linear. This is the goal of any control valve. This is why you don't take a giant full-ported ball valve from Home Depot, stick a motor on it, and throw it on your coil. Okay, other type of position control valve would be the globe valve. I think we're all kind of familiar with it. It's a linear valve. You pull it straight up and the plug kind of gets out of the way. The water goes like that. These valves are a pain in the ass for a couple of reasons. One, they're big, they're heavy, and they're expensive to make. The other problem with them is that physics is not in our favor. When I have flow through this, I have higher pressure water coming in and lower pressure water going out. This is by definition. Water only goes from high to low pressure, so it has to go that way. So my higher pressure is trying to push the plug up, and my lower pressure is trying to push it down. Guess who wins? Right? Bigger force, smaller force. So I'm fighting the water and trying to close the valve and trying to compress the O-ring in here to get a nice tight close-off pressure, and it's just a little bit of a complicated mess once you get in there. Do we still use globe valves? Sure, we sell lots of them. We put them into the marketplace. I frankly can't figure out why, but people still buy them. Engineers love to put them in spec. All right, I'm gonna pull back at it. All right, so that's our position control. That's how we did things for like 80 years. That's our standard. Let's flip over to flow control. This was our pressure independent valve. So all of my presentations are like, hey, I'm going to teach for ASHRAE friendly, all kinds of taco stuff over here. Help yourself. So we put everybody's product on here. If you go to an ASHRAE meeting and you present it, you show your product, they yell at you. If you show everybody's product, they congratulate you and thank you for a great presentation. So that's Siemens, that's Bouygues. We don't really care. Let's talk about why the hell do we put a pressure independent valve in a system. There's three really big things that are important about putting a PI valve in a system. And interestingly, all three of these things are completely overlooked by every single piece of software that estimates the building performance in a construction project. eQuest, TrainTrace, Energy Plus, all of them. Forget all three of these issues. Here's what's good about the pressure independent valve. You can buy one that's bigger than you need, but it won't behave as though it's oversized. In other words, you're still going to get the flows you want, even if that valve's 2.5 times the size of what you actually need for any given load. They all have perfect valve authority. I don't expect you to know exactly what I'm talking about, but if you're in a loop with really high pressure, and you have the same exact valve in a loop with really low pressure, they're going to behave differently. Unless you're pressure independent, because they don't care about that pressure, and they do their job. And they're dynamically balanced, which means I don't put a balancing valve next to it, and I don't have to balance that loop. They balance themselves. It's just like a pressure independent VAV system. You don't run around and balance all those things. Now you don't have to do that on your water system either. All right, there's two types of pressure independent control valves, two technologies. I don't know if this is still in the right place, and his head's in the way anyway, so we'll just show it this way. This is what Belimo calls a PIQCV, and this is what we call the EPIV. One of them is a mechanically regulated pressure independent valve. About 95% of all products from other vendors are this style, meaning there's a mechanical regulator in line with the control valve. This, by the way, it's kind of fun to play with if you guys want to pass that one around. Let's talk about how it works. There we go. Make sure we don't leave this here. I took my jacket off on Monday at a presentation, we just picked it up this morning. Okay, so this is a cutaway of the valve. So what we're looking at is flow rate goes this way. In a mechanically regulated PI valve, what we're going to do is we're going to use a regulator ahead of the control valve part, so clearly ball valve. We're going to use this regulator to make sure the pressure drop across the ball valve is always the same. Because when I said to you before, how much water is going to go through this hole, and we all went, I don't know. If I say how much water is going to go through this hole if I'm pushing on it with a 4-pound pressure differential, we should be able to calculate how much water goes through there. And that's the whole essence of this valve. So I'm going to take a look at pressure before the valve and in the regulator and after the valve. And then there's a regulator in here and a spring, and as you're playing with it, you can push it all around and do funky things with it. But basically, those two pressures are going to activate this regulator, just like this. And as they do that, it's going to make sure that P2 to P3 is a relatively constant number. So if I know that there's going to be about 2.7 psi going through this valve, whatever position it's open to, I'm going to make that much water. So I always get this question, isn't that what an automatic circuit setter does? Yeah, it's exactly what an automatic circuit setter does. Here's the difference and why the automatic circuit setter does not make your regular control valve pressure independent. The automatic circuit setter doesn't have a valve, it just has a hole, which means you can control one flow with that device. With this device and an actuator on it, you can control any flow along that characterization curve. This is a control valve. The other one is a flow limiting device for one single static condition. Okay. This is a completely different type of technology, right? It's exactly the same. So this came off someone else's website. I think it was Danfoss, I don't know. Somebody had a cutaway, and I was appreciative because we can show that the technology is the same. It looks completely different. It's based on a globe valve, right, instead of a ball valve. But there's your globe valve up here. Here's your regulator down here. We've got P1, P2, and P3, and there's a little channel they bored through the valve here to sample this pressure out here to get on the other side of the regulator, to bounce this thing out underneath the seat here to make sure the pressure drop through there is always the same. So if some other valve vendor comes in here and tells you that they have figured out this different, more clever way to be pressure independent, tell them physics. Can't argue with physics. There's just a couple ways to do this. The essence of it is I need to make sure the pressure drop across the control valve doesn't change. If it doesn't, I can tell you what the flow is at every position. Okay, here's the other way to do it. If they come in and they tell you doing it this way, you don't have to yell physics at them. That would be weird. Okay, this is an electronic pressure independent valve. So this is an ultrasonic flow meter, and that is a ball valve. And if you are familiar at all with a VAV box, this looks an awful lot like the air side on a VAV box. So I'm going to go ahead and measure, come on. There we go. I'm going to measure the flow rate, doing 23 gallons a minute. I'm going to talk to the actuator. The actuator is kind of leading this parade. The actuator is getting a control signal from the automation system. It's got that little curve right programmed into it. It goes, okay, 23%, let's go 23% up that curve. What's that flow number? 28 gallons a minute. Oh, we're only doing 23. Hey, ball valve, open up a little bit. It's that simple. And then it sits there, and if the pressure raises or lowers, the actuator's just going, hey, what are we doing now? What are we doing now? It's like your kid on the way to Christmas. What is it? When is it? When is it? When is it? When is it? We'll get there. And so it'll make little corrections, and it'll keep you at 28 gallons a minute until you get a different command from the automation system, and then it'll do something different. That one's easier to explain. All right, I lied about the part where there was only a little bit of physics. Let's talk about static balancing. Has anybody ever heard this term? Because we invented it. And it doesn't really mean anything to anybody else. Static balancing is called by most everybody else balancing. But we call it static balancing. Somebody tell me what condition do you put a building into before you balance it? Yeah, everybody's doing a bunch of this stuff.
Yeah, how long?
We're going to crank those pumps all the way up. Yeah. We're going to open the control valves 100%. What are we simulating when we do that? You already kind of said it. We're simulating the design day, the peak day, the max this bitch is ever gonna do, right? We got this thing pinned all the way out. We're tuning the building for the worst case scenario. Why is that not a static balance? That's one condition under which this building is balanced. What's the effect of that? Well, let's talk about valve authority in the context of this balance. So I told you I'd tell you what valve authority is. It's really quite simple, even though all these nerdy people tell you it's complicated. It's the pressure drop of the control valve divided by the available pressure drop in that branch. So I'm a visual guy, so let's just look at it this way. It's the pressure drop of the control valve divided by the available pressure drop in that branch. What percentage of the available pressure is being used by the valve? The more pressure the valve uses, the more authority it has, or the more in control of the outcome the control valve is. What we don't want to have, so what's our pressure consumers? We got a control valve, we got a coil, we got a balancing valve, we got a bunch of other stuff I don't really care about. What I don't want is the balancing valve to have authority. Like I got a 25-pound pressure drop on my balancing valve, and my control valve takes a 4-pound pressure drop, I'm in trouble. Here's why. Let's take that guy and give him some friends, and then we're going to pipe them all up in the sort of traditional way. This is called direct return piping system. And all that means is that when we pipe the water out, I have high pressure here. It's coming in from wherever we're getting this water. The highest pressure in this screen is right here on the inlet to that guy. And then I drop pressure as I go out. And then as I come back, I drop pressure more. We always flow from higher to lower pressure. We can't reverse that. What the net result of that is that the differential pressure over here might be 10 psi, but as I go further this way, the difference between the higher pressure inlet line and the lower pressure return line gets bigger and bigger as I go that way. So I might have a profile that looks something like that. So I have 10 psi at this, we'll call this the far zone, and I got 20 psi at the close zone. And for this conversation, we'll simply ignore the middle of the building. So we send a balancing contractor out and say, hey, go ahead and balance out this system. And they go out here and they go, okay, control valve, that's a 4 psi. We'll say it's sized perfectly. By the way, every piece of equipment here we'll just say is exactly the same so that we don't have too many variables. So I got 4 psi here, maybe it's a 4 psi coil, so we're going to get on that balancing valve, turn it a couple of times, and the flows will then work out, and we'll use up all 10 psi. Cool. If we calculate valve authority, it's 4 psi over the valve, 10 over the loop, 4, 10. I got a 0.4 valve authority. The ASHRAE handbook, if you spend any time reading that guy, that's good for sleeping. The ASHRAE handbook says things like an appropriate valve authority or favorable valve authority is in the 0.4 to 0.5 range. I got news for everybody. The only time you're going to get 0.4 or 0.5 valve authority using traditional valve sizing is in this last zone at the end of the loop. So as I go this way, the control valve stays the same. But the pressure gets bigger, right? I didn't size this control valve for 10 psi because I got a whole bunch of extra pressure down here. I mean, you can, but you can't. I'll explain why in a second, because that seems contradictory. So for 4.4 there, that means I got to get 12 pounds of pressure drop. So I give this class to consulting engineers every once in a while, and they always go, well, why can't we just size it so that they all have proper valve authority? Well, how would you do that? You'd be like, oh, well, I got 20 psi out here. If I size this for 10 psi pressure drop on the control valve, well, then it has a 0.5 valve authority. And I go, oh, that's great. How do you know this number? When you're sitting around at your computer and drawing crap and selecting things, how do you know what the pressure drop is in this branch? And they go, oh, never mind. I kid you not, this guy does tons of takeoffs. He'll send it to me while. Do you understand this spec? I'll open the valve spec. All valves shall be sized using valve authority method. Call him back and ask him for the pressure drop on every branch in the building. And then we'll get right on that. How do I get 12 pounds of pressure drop? This is the key to this whole thing. This is why this is a mess. The balancing valve is not a particularly smart device. The balancing valve is an orifice restriction, right? The pipe's this big, you put the balancing valve in, you crank it, it goes weep, 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 weep. It makes a smaller opening, and then I gotta shove that water through a smaller hole. And when I do that, it costs me energy in the form of pressure, and I take a pressure loss. Okay, So for this example, we're going to use the pipe as an analogy for what this guy is doing. I need a 12-pound pressure drop. So I crank all my valves open, pumps up to 100%. I got 100% of the water. It's flying through this balancing valve. It's taking almost no pressure drop at all. Balancing contractor goes in there, cranks the handle a bunch of times, shrinks the opening. I push 100% of the water through that smaller opening, and I get a 12-pound pressure drop. I have tuned the building to the design day. What happens when there's only 20% of the water? Let me ask the question differently. Is this opening small when compared to 1/5 of the original amount of water? Yeah, it's not. We're not cramming a lot of water through a small opening. We're putting a little bit of water through a small opening. And so it doesn't cost us a lot of energy in the form of pressure. It costs us a very little amount of energy in the form of pressure. And my 12-pound pressure drop is not happening. So some of you are sitting there and going, okay, 20%, that's kind of on the low end. What's the big deal? I made a big deal out of this before because it fits into my presentation nicely. 20% of the flow is half the friggin' load.
So hunting.
Yeah, so hunting, yes. We'll get there in a second. How about this? We talked about the automatic balancing valve, or the automatic circuit setter, the flow limiting device. I've never met a device that had more names than this thing. Everybody gets confused. Wait, is that the same as? Yes, it's the same. Okay, so this is a tiny little valve. Maybe it does 3 gallons a minute. We stick it in that system, and you cannot put more than 3 gallons a minute through there. It's good for that. But if you only want to control 0.8, it's literally doing nothing. It's just letting water sail through there. 0.8, 1.2, 1.7, 2.4, 2.8. Oh, I start to get a little pressure drop in here. 3, that regulator kicks into action, and it looks just like that valve we passed around, making sure that we don't pass too much water through there. There's a gentleman named Kent Peterson. He is the P in P2S engineering. And Kent agrees with me, and so I quote him. He wrote an article a few years ago that said flow limiting valve essentially does nothing when the flow is below the design, as when the valve is throttling. So when you're using the control valve as a control valve, this thing's not doing much. I used to get into arguments with people all the time, and they'd say, hey, if I just put a regular control valve and an automatic circuit setter next to it, it's pressure independent, right? And I said, as long as you don't care what happens between closed and full flow, you are correct. But if you want to actually modulate that thing, you're missing the boat. All right, we'll go back to our building. No, please, come in. Don't worry, you don't even have to duck or anything. We'll go back to the building. We're going to turn all our pumps way down. Remember, we're at 20% of the flow. That control valves are all halfway open. We're doing a nice mid-range load here on all of my spaces. What happens to my pressure now? I've got 10 psi out here. This was supposed to take 2. It's not. The coil, by the way, is a pressure-dependent device also, so we turn that flow down into way less than 4, but we don't want to make the math too complicated, so we'll just say less than 4 over there. And all of the rest of the pressure, whatever's not consumed by the balancing valve, whatever's not consumed by this coil, well, the valve's just an opening. When you put it in a position, it's just an opening, and now I've got more pressure on that opening, so I get a little bit more flow. In this case, I'm not tremendously overpressurized, and if I'm being honest, this last zone is always well behaved from a control standpoint. If you spend more than 10 minutes tuning the loop on the last loop in the zone, it's time to find a new profession. What happens when I go back there? I was supposed to take a 12-pound pressure drop. We made a big deal about that, but it's only 2 pounds. And my coil's taking less than 4, and so my control valve takes a substantial pressure drop from what we bought it for, what we sized it for. And by the way, we made the assumption for this exercise that all our valves were sized correctly. I got a whole other presentation that talks about how you can never size it correctly. It's always too big. But even if it was the right size, I'm putting almost twice as much water through here as I meant to. Now we're hunting. Why are we hunting? Well, I just need a little bit of cooling in this space. So my leaving air temperature was like 55, it creeped up to 56, 57. Let's open that control valve a little bit. We'll open the control valve. water's getting, whoa, 57, 56, 55, 54, 53, whoa, close the valve. Creeps back up, open it. What else is happening every time I open that control valve? Turning that fan on. Now you got, not only are we hunting, we got an unstable loop, we got an annoying space to be in. So let's hope this isn't somebody important's office. Okay. What if we dynamically balance the building? We said PI valves are dynamically balanced. What the hell does that mean? Well, let's take our fan coils. We'll put 4 of them in a row. You'll notice there's a PI valve in each of those. And while we have all these different pressures, we'll notice there is no more balancing valve over here because we cleverly didn't put it in and save the money of installing that guy. And I have low pressure there and high pressure there, and we don't need to talk about pressure anymore because all of the valves are pressure independent and controlling directly to flow. Now I have the proper flow going into each one of these coils, regardless of whether I'm close to there, far out here, or whether I have a very high load or very low load on this space. I'm no longer dependent on a relatively unintelligent balancing device that's the pressure hog in zones like this. We passed that valve around. The key about the valve that you were playing with was that it adjusts itself to the conditions that are happening right then and there. Think about how silly it is to use a manual balancing valve. You dial it up one time and you never, hopefully, touch it again. How could it be right most of the time? I always ask consulting engineers, how many design days are there in a year? Because that's what they design the whole friggin' building around. And the guys are always like, oh, 4 or 5, blah, blah, blah. I was giving a big class one time. The guy in the back goes, 13 hours. Okay, that's really specific. Go on. He's like, no, you gotta understand, it's only 2.7 hours and we calculate 4.3 days per year, because when is the design load? It's in the middle of the afternoon, right? The sun load is the big deal. We don't, on the design day at 8 a.m., we're not at design condition. So I don't know how many hours are in a year, but way more than 13, right? We're talking about less than 1% of the time our building's tuned to. Here's the other reason that we should never use manual balancing valves, and I hope to never run into a guy who sells those because I talk shit about them all the time.
What about for coil banks?
Yeah, no, there's value in them.
Yeah, I'm just...
Yeah, and the flow limiting valve is a tremendous valve for very certain things, just not this.
I'm not saying.
Here's the problem. So one of the things that Carlos and I do a lot when we're not talking to engineers and contractors is we talk to guys in dirty overalls in the basement of big buildings. And I'm like, hey guys, what's going on? And we'll be talking about things like, how do you do your troubleshooting on this? And I asked a guy once, we were talking about energy valve, and I wanted to get him to tell me that he had a little bit of trouble figuring out what to do if his space wasn't making temperature. Because the energy valve can like see all kinds of things that are going on, and I was going to sell him real hard on what a great maintenance tool this is. So I go, okay, you go up to air handler 7 and you're not making air in that space. What do you do next? And I wanted him to tell me that he couldn't figure out how to check whether there was flow or not through the pipe. That's what the usual answer is. He goes, that's easy, I just go open that balancing valve all the way up. Okay, you win, man. All right, here's another interesting way that pressure-independent valves change the whole way a building works. We call this hydronic isolation. So let's say we have a nice little building here, and it's on some kind of campus. So there's big chilled water loop somewhere, and it's just dumping water into this building. I don't care how it gets there. And for simplicity's sake, we'll say there's 3 thermal zones. There's like an air handler on the 2nd, 4th, and 6th floor or something. It satisfies 2 floors apiece. And we'll use our same diagrams here that we're used to. So we have a variable speed pump in the basement that's taking that chilled water and pumping it up. And I've got these fan coils or air handlers. I've got standard pressure-dependent control valves and balancing valves in each zone. This is my least favorite thing about every building that doesn't have pressure-independent valves. They don't act how we think they should. So, let's put our pressure array in. We'll use nice round numbers so when we play with them, nothing gets crazy. And we have this building here, and on this first floor, it's full of it. It's like a big consulting engineering firm. So on Friday at noon, they just go home. They don't work Friday afternoon. And the building manager, they do this every Friday, so the building manager's aware of this, and he sets a weekend setback for those 2 floors. Good idea, right? Let's just shut the fan off, turn the valve shut so we're not wasting energy. For the sake of this argument, let's just say everything in the rest of the building, it goes unchanged. Thermal load's the same, nobody leaves for lunch, everybody just there. All right, so we're gonna close this valve. What happens when we close this valve? Well, a couple things happen. The first thing that happens is this pressure goes to zero. If there's no flow through there, there's no pressure drop. Well, all that pressure now goes downstream a little bit. So I'm gonna over-pressurize these two other zones. All the people in there just sitting at their desk working away, nothing's changed. When I overpressurize these two zones, two things happen relatively simultaneously. The first thing we'll look at is that I've put more water I meant to into these coils, and I've probably disrupted the air temperature. So we were doing 55-degree air, everything was fine, and then we went, oh, 54, 53. What happens when I hit 53? Oh, the controller says, nope, the air's too cold. Let's dial those control valves a little bit closed. Okay? Modulating those valves a little bit closed to get that air temperature going back up. But at the same time, the pump says, no, I'm supposed to do 10 psi up there, and that's 15, so I'm going to slow down. So to recap that, what I just did was slow down the pump, created less head in the system, and closed the valves at the same time.
So
what happened? I just starved all my spaces. So I went 53, 54, 55, we were real happy we got there, 56, 57, god damn it. So we send a signal back to the valve to open it back up. When I do that, this pressure drops again. That was from 10 down to 8 or something, and the pump now has to crank itself back up a little bit to catch up with the, oh god. Okay, so it's good, we'll get there, don't panic, it's okay. It's just like, it's gonna come to stasis and it'll get there. Every building in the world, for the most part, does this. Here's why it's interesting, or here's why it's important. How many control commands, how many product movements occurred? We didn't even look at the fans and the dampers. How many of them occurred in two spaces where we repeatedly said the load was unchanged, just because something changed somewhere else in this system? Okay, so I always think, I did this once, and some guy's like, but that system has no diversity in it, it's unrealistic. Wow, okay, true. What if this building had one giant air handler on the roof and 25 VAV boxes in it? And I have hot water reheat valves on each one of those air handlers. And each one of those 25 valves has a regular control valve and a balancing device on it. Do you think any of those valves ever stops moving? Yeah, unless it's closed. Okay.
If you had reverse return piping, wouldn't that
2 days in a row I got this.
Don't forget your jacket.
Yeah. Like having a Groundhog Day week. So with reverse return fix this. Reverse return fixes the thing from the previous example. Actually, it wouldn't in this case because we're still going to overpressurize those two zones. So a reverse return system, for those of you who go, what the hell are they talking about?
First in, last out.
Let me do this where it's cleaner. So here we have this very pressured. So instead of returning the water this way, we would eliminate this piece of pipe right here, or actually this piece of pipe right here. And when the water returns, instead of going back to the pump, it goes that way. And then you put an extra loop of pipe that comes all the way back around. And the idea is if you did it perfectly, let me rephrase this, on paper, you can make it so this is 10, and this is 10. And then it fixes some of those issues. There's two main problems with a reverse return system. One of them, they're really complicated to pipe and they cost a crap load of money because you got to buy 50% more copper. And the second part is that they're much easier to design on paper than they are to get exactly how you want them. And most designs where they have reverse return systems, and you should never have to balance a reverse return system, always have balancing valves in them because you get like 10, 13, 9, 14, and you got to kind of dial them in. And then you still have little valvulatory problems. Look, it's way better than a standard system, but frankly, for the cost of putting PI valves in and the headaches that go along with it, it's so much less expensive and simpler the other way. That said, scientifically valid point. Thank you. All right, so we have the same building. We scrap our balancing valves. We put the, oops, sorry. Everything's ringing. We put the balancing valves we toss, we put PI valves in every zone. Consulting engineers go home, we close down the zone, we overpressurize, and the flows are unchanged. We're done, right? The pump will get there, it'll dial itself back down, so that goes from 15 to 10. And we've absorbed the extra pressure, we've kept the proper flows, we haven't disrupted the temperature in the space. This building behaves, this building behaves like we think it should. Like, it just makes sense. The other one does a bunch of crap we weren't expecting to happen until we look at it and then we go, oh yeah, I guess that makes sense, it would do that, wouldn't it? All right, one last little thing before we get you out of here. We'll talk about the smart valves in real short form, and then if you want to learn a lot more about that, we'll come back at another time and kind of bring one, plug it in and take a look at it. It does all kinds of cool stuff. So the idea behind smart valves, this one's called the energy valve. That's Belimo has one. We've been selling the energy valve for almost 10 years. We're quite grateful because in the last 2 or 3 years, a few competitors have started to put them into the industry. And it was weird because I just said we're really grateful about that. But we are, because for 8 years, we go to people, they go, we really like this. Does anybody else make one? We can't sole source, blah, 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 blah. Or we won't put that in our spec because of this, that, or the other. But we've been doing this forever. It's all about coil performance. So if we talk about a coil, we're going to talk about something called coil delta T. At delta T, what we're talking about is the difference between the temperature that arrives at the coil and then what the return water temperature is. And the higher that number is, the more stuff the water did when it was in there. Like if I took 42-degree water and put it in this coil and it came out at 43 degrees on the other side, it didn't absorb much heat while it was in there. But if I put it in at 42 and it comes out at 58 or something, I pulled all kinds of heat out of that air. And this coil is designed for that. When I buy a coil or specify a coil, it's going to have a flow rating, a BTU rating, and a delta T rating. And all those numbers are mathematically linked together to get a nice heat transfer. So if I have low delta T at my coil, which is super common because I have a giant ass control valve on a humongous coil and it's April 14th and we had outside economizing air coming in for most of the day, so there's like this much load in the space and I can't get a valve to slow the water down just at all, and so I'm blowing an enormous amount of water through my coil for a tiny little load, and that's how you get low delta T in your coil. I like this guy, he just nods when I talk. So the inefficient, wait, what'd you say? But low delta T means I have an increase in flow rate for the load. Quick reminder, the load is defined by the space, not by how much you try to heat or cool it. The load in this space is because we got a lot of adult males in here right now, and it's, right? That's why we would have to try hard to cool this space. If we all get up and leave, and we blow the same amount of air into this space, we're not going to have the same effect. And our efficiency will go way down. There is a right amount of water for any given load. If we could figure out what it was, we could choose to use it. That's really what we're going to do here. Obviously, if we pump more water, we waste energy in the pump. The plant doesn't like it when you return cold water to it. There's all kinds of advantages, or disadvantages. The Belimo energy valve is a fully functioning BTU meter. If you don't know what a BTU meter consists of, it's a flow meter and 2 temperature sensors that measure the temperature of the heat exchange, or the delta T. So we're measuring flow with our ultrasonic flow meter. We've got a temperature sensor in either piece of pipe, and it can monitor how much heat exchange goes through that guy. The energy valve has something called a delta T manager in it. I can set a low limit for delta T. Basically what I'm telling the valve is if you can do heat transfer effectively and hit the leaving air temperature you want at 12 degrees or higher, knock yourself out. If you're going to do it at 12 degrees or lower, we're going to have to interfere. So what does the valve do? So this is my coil curve. We looked at that earlier. This is the delta T curve. Has the opposite shape, but really for the same reason. You know, that slow water goes in pretty cold, comes out nice and warm on the other side. So let's say I get all the way out here and I've overflowed that coil. My delta T threshold is at 12, but I'm down here around 10. Well, the energy valve's going to say, no, I'm not okay with that. It's going to take control away from the automation system. It's going to continue to look at what the automation system's asking for, and while it's doing that, it's going to start reducing the flow to that coil. And it's going to continue to reduce that flow until it achieves 12 degrees of delta T. And if we have chosen the 12-degree value appropriately for the equipment and the space it's trying to cool, we will have no effect on the leaving air temperature, because I'm going to go horizontal through that point cloud. That point cloud represents all of the different heat transfer values, and if it's a straight line going left to right, it all lines up with a certain amount of BTUH. The sneaky fact about this is that I can cool air at different BTUHs, I can produce the same amount of BTUH extraction from the air at different flow rates by varying my delta T. So I said something like you have to pick the right number, and here's why. Let's say I was like, nope, I want 16 degrees of delta T off this coil. Well, I'm going to break this at that point. I'm going to reduce the flow so far that I won't be able to produce enough cooling for the larger loads in that space. And so this isn't like fantasy camp for coils. What we're trying to do is figure out exactly the best that this coil can do and then force it to behave at its design condition even when the loads are not at design conditions. One last slide and then we'll let you go. This was a case study that was done at an IBM facility in North Carolina. So they bought a bunch of energy valves a while ago now, and they put them in, and they did this academic study, and then they just sent us this one slide and like, look what we did. Cool. But it's actually really good information. So this is tons of cooling across the x-axis. This is the load in space. And then this is the chilled water delta T of the air handler coil. And all of this data comes off of air handler B500A3. What they did was my set of stairs. They put it in position control mode here. They turned off all the smart stuff, then just measured. BTU meter, in play, all the smart stuff in there. And when they did that, they had loading 45 to maybe 75 tons. And I got a whole bunch of reports here from like 4.5 to 7.5 degrees of delta T. And in fairness, they got all this stuff over here too, which is much nicer than what they got down here. A couple of weeks go by and they tinker with it, reprogram the valve so that it's in flow control mode. It's now pressure independent. We're getting roughly the same loading, but now we're like 10 degrees of delta T. I got a little secret about flow and delta T. They are inversely proportional for a given load, which means that if one goes up by a certain amount, the other one has to come down by the same proportion in order to make them equal. Which means if your delta T is half of what you expect it to be, you're flowing twice as much water as you need. Going from 5 degrees to 10 degrees of delta T is an enormous change. They put the delta T manager on. This was a 16-degree Fahrenheit coil. We expected to be able to do this. They actually weren't able to satisfy the space at 16, so they reprogrammed it for 15, and we got a whole bunch of 15 all day long with delta T management in play. So what does this mean? Let's normalize this by looking at a single load point. We'll look at 60 tons. It more or less runs through the middle of all of these data sets. If I wanted to do 60 tons of cooling in position control mode, I got 6 degrees of delta T, that requires 240 gallons a minute. So put 240 gallons a minute through that coil, boom, 55 degree air, everybody's happy. Except the plant guy, he's not happy. 60 tons of cooling, 10 degrees of delta T. It's almost 100 gallons a minute less to cool the exact same space, the same 60 tons, with the exact same piece of equipment. Remember when we started, I said, whoa, that's a different, the valve just interprets the control signal different. This is a how much should I open the valve, this is a let's control to 144 gallons a minute. When we go to 15 degrees of delta T at 60 tons, that's less than 100 gallons a minute. We were using 2.5 times the amount of water we needed to cool that space for 60 tons during the course of this experiment. The equipment was unchanged. The space was unchanged. The only thing that changed was how the valve interpreted the control signal, and then we put an override in that said, just forget you guys, we're just going to demand 15 degrees delta T. Look, we do a bunch of case studies that look like crap when we're done with them, and we throw them in the garbage. We only show you the good ones. So if you're sitting there going, that's not believable, well, it's believable, it happened, it doesn't happen 100% of the time. The reason I like to show this one, and the reason I'm willing to tell you that we don't have all great ones, is because this is just a proof of concept for me. I just sat here and told you that we can make your delta T way higher and choke the flow way back into your coil, and don't worry, we'll cool your space, trust me. And here I'm using 40% of the original flow value and still offsetting 60 tons in the same space. And that's what makes this really impressive, and that's what makes it viable as a solution. So cool, let's close out there. Do you guys have questions? I just bombard people with information. Do you have questions as we've gone through?
What's the cost difference if you upsize to a smart valve versus just a standard flow control and down-to valve?
So the short answer is that's a long answer.
Okay.
It depends a lot on the sizes and stuff like that. So,
1 inch.
I don't know, we could look that up.
Okay.
If you want to go directly from this to this, you're going to get a little sticker shock on that. What we meaning Belimo, what we have always done is make the argument from here to here first. The difference from here to here is about 15, 20%. Is it 20% now? It's about 20%. And then I'm going to be like, but you get a BTU meter on every single piece of equipment, and you can network them. They're all BACnet, and I have an IP server on each one, and you can do all these things. And they're like, holy crap, for that, it seems worthwhile. So the argument's from here to here, but remember, this was the 100 gallon a minute per difference from here to here. Here's the other really sweet spot. So this guy, love this valve. This guy here should be on every reheat coil you ever install for the rest of your life, every little fan coil you have, anything that's less than like 9, 10 gallons a minute, this guy. Why? You cannot buy a CCV, the regular valve, and a balancing valve for less money than this. You're installing one device instead of two, and you're getting infinitely superior control. So when I'm talking to a building owner, they're like, oh, it's a big project, we're going to put PI valves and everything, it's killing me. I'm like, you only have like 8 or 9 big air handlers. All of these are free for you, not free to you, but they're not increasing the cost of the project. And yeah, you're going to pay a premium when we get to these bigger valves, but think about what you're buying. You're buying a huge amount of energy savings, building transparency, and all these other types of things. So don't let your customer get pushed off by the idea that I've got 95 valves in the building, 75 of them look like this, and don't cost very much to put in, or actually are saving you dollars on the overall project cost. That's where we can get people to start paying attention to us. Yeah, if I go in and I go, every single one of these is 50% more, they'd start going, oh my God, I've got so many valves in the building, and this is a heartache, and this, that, and the other thing. Everybody likes to make tiny generalizations about stuff. Sometimes it just takes a minute longer to have a discussion about the reality of it. Carlos had a great talk with a customer who was trying to VE out a whole bunch of PI valves in some project. And he sat down with the building owner and he's like, the valves in this project are less than 1% of the total cost of your project. And you're trying to knock $15,000 off the cost of, it was like a $50 or $500 million project, and you're worried about $15,000 to VE the PI valves out of the system? When we start talking about that scope and scale with people, they start to understand there's a lot of value in this really incremental cost that they have put in. Now, if they're going to buy one globe valve to replace it out in the hospital, and we're like, that costs $2,000, and this energy valve's $10,000, they're like, whoa. Then I always ask them, well, what does it cost to install that globe valve? Oh, that's a pain in the ass. That's like $5,000 right there. Okay, costs way more to install than buy the valve anyway. All right, questions, thoughts, or comments?
I had a question.
Yeah.
You showed a study right there. Has anybody done a study on energy savings and simple payback?
So you should know. So we can apps. So here's the issue with simple payback. If you're building a new building, I can't tell you. Because you're probably thinking before you start building your building it's going to work great. You're wrong, but you think it's going to be fine. The only way we have an energy savings calculator, we can pull an ROI number and all those fancy financial metrics. I can't remember what they
They're
are.
on the website.
Yeah, we have it on the website. Give your card to Carlos or send him an email, he'll send it to you. But it requires us to say this is what our delta T is today, and this is where we think we can get it. So when you're building a brand new building, they go, it's 14-degree coils, of course we're going to get 14. No, you're not. But I don't know how to guess what you're not going to get either. It's an inherent problem with the way we model everything. Our models are all based on the design day also. We'd be happy to work with you on that a little bit to try to put a number. There are some guys that don't want to talk about it unless we can put a number on it. So we can put a number on it, and we tell them we're throwing darts a little bit. We're making a lot of assumptions, but this is what this should look like. If that's what it takes for them to feel good about what they're buying, we can absolutely put that together. I always tell this story, and if you have to go, please just leave. I always tell this story about selling energy valves, because like they give me all the new people that work at Belimo, they're like, holy crap, how do we sell this thing? I always go into the hospitals, love to sell energy valves to hospitals, big complicated campuses, their hydronic systems are a mess. And I go in there and I go, hey, let me ask you a question, because the energy valve's got a BTU meter built into it, you can see that thing, we can create advanced metrics with you that'll just tell you when you're supposed to clean out the filters and the strainers and all that stuff. You don't have to wait till we're disrupting air temperature. I go, is it more expensive if that gets messed up on Tuesday afternoon during surgery than if it, you can swap it out on a Saturday at 3 o'clock in the morning? What does it cost to close your surgical suite for 2 hours? Oh, it's like $43,000 an hour. So for 2 hours, that's I didn't even hear what you said, $80-something thousand? Yeah. Now this $10,000 valve doesn't seem so expensive. There's a guy up in San Francisco, he's energy savings, and he uses the concept widgets to digits. And you've got to take what's important to them and put it into a value that makes what you're selling seem a lot smaller. If all I did was try to sell on ROI on energy, I would get bogged down a lot because you got to save a lot of energy to buy a $6,000 control valve. But if I could tell you that you're running a hotel room and I got to close 2 of these ballrooms for a couple of days to do maintenance on them that I could have prevented, what does that cost you? Oh God, no, we got to cancel this whole conference and that's going to cost tens of thousands of dollars. This stuff starts to be real simple. And it gets out of this energy budget stuff and into operational budgets where there tends to be way more loose dollars. So we call it the energy valve. I'm not trying to lecture you guys. Belimo did this wrong for 6 years before we figured this out. We were like, hey, let's get all the energy managers in the country. And they're like, oh my God, we're still selling LED light bulbs. Get out of here with that stuff. And once we started realizing the functionality of this thing, that you could talk somebody into just having a building that's easier to run, I was asking, how much you guys pay your guys overtime? Like if they're not in the room. Are you guys paying your guys overtime? What if we could just make that go away? Like over a year, like what's the line item number for the year? And what if we made that go away? Oh, well, now we're talking about things. So just stuff to think about. Or tacos, enjoy yourself.